Hey guys, today's video is going to be pretty short. We're currently in our rates of reaction unit, and we've already talked about how both concentration and temperature can affect the rate of reaction. And so today we're going to take a look at two other variables we can kind of manipulate as chemists in order to affect the rate of a reaction. The first we're going to focus on is the presence of a catalyst, and the second we're going to take a look at is surface area. So the first thing we're going to take a look at is how a catalyst can impact the rate of a chemical reaction. And we're going to do that by studying the decomposition of hydrogen peroxide. Hydrogen peroxide is a topical antiseptic that you can pick up at Walmart, Meijer, Jewel, wherever. It's commonly called witch hazel. Its formula is H2O2. And this is a pretty straightforward decomposition reaction where it breaks down into liquid water, also gaseous molecular oxygen there. And this reaction is spontaneous, right? If we were to go through and actually calculate the change in entropy, we'd find that it was positive, which is favored, thermodynamically. If we were to find the change in enthalpy, again, we'd find that that was negative. It's an exothermic reaction, again, preferred by nature. So actually at all temperatures, this reaction is spontaneous. It has a negative change in free energy. That being said, though it is thermodynamically favorable or spontaneous, the reaction really doesn't proceed to a noticeable degree, right? It's quite slow without the presence of a catalyst. And if a reaction is thermodynamically favorable in terms of delta G, but we don't really see it occur at a noticeable rate, it's likely because it really has a high activation energy. So this necessitates the presence of a catalyst. When it comes to catalysts, to be a catalyst, you have to do two different things. The first thing you have to do is to lower the activation energy of a reaction, right? And in doing so, you speed up the rate at which that reaction will take place. Besides this, catalysts are initially consumed, and then they are reformed. So what's special about catalysts is that they actually don't get used up, okay? Now, the reaction we're studying, it would appear as though it takes place in a single step. What is more than likely is that it occurs in maybe two, possibly even three steps, where what we don't have written in this equation is actually the presence of several intermediates. Maybe this decomposes into a intermediate, and then that intermediate in turn, finally kind of forms our water and our oxygen. Okay, but no matter the mechanism by which the reaction proceeds, a catalyst is always going to be consumed and then reformed. As far as how this impacts our progress of reaction diagram or perhaps our kinetic energy distribution curve, the only thing that really changes here is that, again, a catalyst will lower your activation energy. So the distance between your, say, reactants and your transition state, the amount of energy to reach that transition state or that activated complex is actually be substantially less than the activation energy without a catalyst. Okay, and the way this manifests in our changes as far as kinetic energy distribution curves go, or what's called a Maxwell Boltzmann distribution curve, is that if we were to plot our activation energy, without a catalyst, so we'll say without a catalyst, we find that the area under the curve, there's only, the small subset of molecules that actually have sufficient kinetic energy to overcome the activation energy. Yet if the activation energy kind of slides down to the left here, right, because we have the presence of a catalyst, as indicated by this smaller interval here, we now have a much larger area under the curve, much larger number of molecules that can react immediately, and thus the rate of the reaction is faster. In the demonstration you guys are going to see when you pull up the YouTube video that I've linked out from Flynn Scientific, we're going to take a look at a 30% solution of hydrogen peroxide. So that means that liquid hydrogen peroxide has been mixed with water at about a 30% concentration. What we're using as a catalyst is going to be our ferric ion, our Fe3+ ion, and we've done that by introducing it in the form of ferric chloride at a 0.1 molar concentration. Okay, so you'll take a look at that video, and you're going to see, the pretty significant effect that a catalyst can have on the rate at which a reaction occurs. The next thing I want to focus on today is what surface area can possibly do for a chemical reaction. So The reaction we're going to take a look at is actually the combustion of lycopodium. Lycopodium is a spore from a moss. So basically it's just organic matter. It's very, very fine, very, very small as far as being like a small particulate size goes. So it's really good at burning. So we'll start off with a question. What can burn better? What's going to yield a better fire? If you have any experience building fires, if you try to stack a number of logs on top of each other and light this thing on fire versus, say, maybe more like a teepee type structure where you have some smaller kindling at the bottom, this is certainly going to burn quite a bit better. And the reason why is because we have a lot more exposure to oxygen, right? We've increased the surface area by creating this teepee. We've exposed a lot more of the wood to oxygen, as opposed to in this scenario where by stacking them, we've actually limited the surface area that's in contact with oxygen at any one given time. Which again, normally we wouldn't start building a fire just like this. We'd have that small kindling, some small pieces, some small twigs, things of that nature. Just kind of get this thing going, okay? When it comes to surface area, we're going to say that an increased surface area increases the rate of a reaction or perhaps a process. So maybe we're not, burning something in the presence of oxygen. Maybe we are, say, dissolving something in water. And the reason it does this is not because it's increasing concentration, right? If you have, 1 mole of a compound, whether it's ground up or whether it's in kind of a solid clump, that's not changing the pure amount. What it does change by altering the surface area is the amount that can immediately react or kind of immediately or initially interact. So as an example, we're going to walk through some math here. And the question now becomes, what's going to dissolve faster, right? So let's say we have a cube of sugar, or perhaps we have sugar granules, and we're just going to do a quick experiment to see what dissolves faster as we agitate that solution or stir that solution. So if we have a cube of sugar, right, that measures 4 by 4 by 4, the reason I've chosen to calculate surface area is because if a water molecule is represented by this red dot, in order to dissolve sugar, the water has to physically come into contact with those sucrose molecules. And they can only do so on the surface of the cube, right? It can only dissolve the cube from the outside in. There's going to be a whole bunch of sugar molecules on the inside of this cube that initially are not exposed to water, right? They don't even see water. They're just surrounded by other sugar molecules. As we start to, say, chop this sugar cube up, right? So I'm just going to cut this thing in half. We're presented with the second scenario where we've now exposed, and you can't see this one here, but these interfaces, right? And by exposing these interfaces, we've increased the surface area. We've increased the kind of sites at which water can interact with our sugar molecules. And so what we find is as we do the math for the surface area, we find that it's increased to 128 units squared, whatever those might be, okay, maybe centimeters squared. Finally, we're going to go ahead and cut each one of these things in half, and we're presented with this bottom scenario, where finding the surface area of all 4 cubes together, we find the surface area is 160, right? So again, as we start to take our sugar cube and we start to break it into smaller and smaller particles, what we find is that there's more exposure, right? Water has the capacity to interact with sugar a lot more frequently because areas that were formerly kind of hidden within the middle of the sugar cube are now immediately exposed to water right at the get-go of this dissolution process. Okay. In the experiment or the demonstration you guys are going to observe from Carolina, I believe it's Carolina. Let me check on that. Yeah, I think it's Carolina. They're going to walk you through the combustion of lycopodium, which again is just spores from a moss. Okay, it's just a really, really fine grain combustible material. They're going to burn that in the presence of oxygen. And in order to kind of get this thing going, right, in order to overcome the activation energy for this combustion reaction, like the spark or the what's going to introduce the initial kinetic energy is just going to be introducing a flame, essentially. And this is my depiction of that fire there. So go ahead and watch that second demonstration video as well. And in doing so, you have some nice notes here now on the page, but those demonstration videos are going to really, I think, kind of help you out in solidifying what's going on, first with catalysis and then with surface area in the context of those experiments. while really kind of making sense of your concrete observations there. All right, thanks, guys.